Okay, we'll be doing a calculation about beams, which comes from a question paper of 2024. I think it's the final paper. And it's the calculation about the beams where you have to calculate firstly the reaction left, the reaction right, and then also the bending moments, and then also draw the bending moment diagram. For this exercise, because it might also be asked in any other paper, not in 2024's, but it can be in next year's paper or this year's as well. So we're also going to calculate the shear forces and draw the shear force diagram. Okay, so firstly, what they give us is the beam. And there's a beam with 3 downwards forces or loads going vertically down, and then 2 upwards forces, which is unknown at this stage. So firstly, we should calculate the unknown upwards forces, which is the reaction left and reaction right. So remember that on your question paper, there is a sketch like this given, but you will need to draw this sketch, this beam on scale on your answer paper to be able to get the width of the beam according to the scale that they give us, and then to draw the diagrams from the bending moments after we've calculated this. According to the width that they give us, you will have to draw the bending moment diagram as well as the shear force diagram. Okay, so whenever we do a type of calculation with this exercise or with this question, there's not a specific formula that you follow. It's not something that you get at the back of the question paper where there's a formula page. So my suggestion is always to first write down the heading of whatever you are going to calculate, so that the marker knows what you are busy working out. Remember also to add the question number. Remember, this entire exercise is normally from question 7, forces, where there are different types of forces that you have to calculate, but remember to number this one. So normally it would be 7.1, 7.2, 7.3, and the diagram would be 7.4. But make sure that you number the question according to the question paper, but then also, as I mentioned, add the heading for what you are busy calculating. Okay, so whenever we want to calculate reaction left, you have to work around reaction right. And whenever you want to calculate reaction right, you need to work around reaction left. Okay, so the heading in this case would be working around the moment, calculating the moments around reaction left. So if you are a bit more of a picture person, if you are working around reaction left, that would be the pivot point. So if there is a force pressing down on the pen, this will be the turning point. Okay, so whether it goes up or down, the pen or the beam moves around this point. So keep in mind that this entire beam is in equilibrium. So that means that the force pressing down on this pen times the distance to the turning point, plus the force pressing down times the distance to the turning point, plus that force pressing down times the distance to that turning point. All of those added together will be equal to the upwards force times the distance up to the turning point. So it's the whole time the force times the distance, plus the force times the distance, plus the force times the distance. And remember that force times distance is the moment, or a moment is equal to force times distance. So this is something that you will have to remember, because it's not something given in the formula page. But keep in mind, we are working with moments, force times the distance. So then the units will be Newton meters. Okay, so in order to calculate reaction right, we have to work around reaction left. So we are going to write the heading, moments around reaction left, but we are actually calculating the moments at reaction right. Okay, so we will first, on the left-hand side, or left side of the equal sign, we will put the unknown value. So it's reaction right times the distance. So it's that force, the unknown force times the distance. So that's 2 plus 3 plus 3 plus 2, that's 10 meters. So reaction right times 10 meters. Keep this in brackets. So it's reaction right times 10 meters. Close the brackets, equals to, take note that each moment we are keeping in the brackets. We will get rid of this later, but this will help with the substitution or the adding up of the multiplication and the addition of the moments altogether. Okay, so again, that's the turning point. This is the only upwards force, so it will be the force times the distance. That moment is equal to force times distance plus force times distance plus force times distance. Each time the distance up to the turning point. So you can decide, are you going to start on the outside with the outside force, the one furthest from the pivot point or the turning point, or the one closest. So I'm going to start with the one furthest. There's no downwards force at point E, but there is one at point D. So it's 50 newtons times 3 plus 3 plus 2, so it's going to be 8 meters. 50 newtons times 8 meters. Keep in mind that is one moment, so we're going to open a bracket, write down 50 newtons times 8 newtons, close the bracket, plus, then we're going to write the next moment down. So that will be the next one. We've already done the 50 times the 8. So now it's 75 newtons times 5 meters. 75 times 5 meters. I see I made a mistake here. This is meters and that one is newtons. That one is newtons. And then plus, the last moment will be the 60 times the 2. 60 newtons times 2 meters. I'll just have to write a bit smaller for the next one to make sure it fits in. Okay, so that is all from the beam, from the turning point over here, all the upwards moments, which are equal to the sum of the downwards moments. 1 upwards moment and 3 downwards moments. Now we have to get rid of the brackets, so it will be 50 times 8 equals to 400 Newton meters, because it was Newton times meters, plus 75 times 5 meters equals to 375 Newton meters, plus 60 times 2 equals to 120 Newton meters. So then we'll add all of this together. So it's 400 plus 375 plus 120 equals to 895 Newton meters. Okay, but remember, on the left hand side we still had reaction right times 10 meters. So we'll just add it over here again, just to help with the next step. Times 10 meters. Okay, so reaction right times 10 meters equals to 895 Newton meters. Now we have to get rid of the 10 meters on the left hand side. So that's multiplied by 10, so we'll divide by 10 on the left side, divide by 10 on the right side. So reaction right equals to 895 Newton meters. Keep the units there to help you to keep the units right for the final answer. So divided by 10 meters, and this will give us 895 Newton meters divided by 10 meters equals to 9.5. So it's Newton meters divided by meters. Meters cancels with meters, so we are left with newtons. Okay, so reaction right is equal to 89.5 newtons. So now this is this one. We will add it over here, equals to 89.5 newtons, just to help us with the calculations of the bending moments and the shear forces a bit later. Okay, now we have to calculate or work around or calculate the moments around reaction right in order to calculate reaction left. So this will now be the pivot point. Again, we are working around, emphasis on the around. That is where the pivot point will be. We are working around reaction right. So that is our pivot point over here. So we will say the upwards moments is equal to the sum of the downwards moments. So the upward moments, there's only one, so it's reaction left times 10 meters. That's the only upwards force, so it's the force times the distance up to the pivot point, which is reaction right. So it will be, open the brackets, reaction left times 10 meters is equal to the sum of the downwards moments. So the pivot point is at point E. Upwards moment we've already written down. Now it's going to be the downwards moments, which is 60 times 8 meters plus 75 times 5 meters plus 50 times 2 meters. Each time the distance up to the pivot point. Okay, and the pivot point is in the heading of moments around reaction right. That will be the distance up to, or the point up to where the distance will be written down in the formula. So the first one is 60 times 8 meters. Open the bracket, 60 newtons times 8 meters plus, open the bracket again. Next one will be 75 times 5 meters. 75 newtons times 5 meters plus, the last one is the 50 newtons times 2 meters. Okay, now we have to get rid of the brackets. So 60 times 8 equals to 480 units will be Newton meters because we multiplied newtons with meters, plus 75 times 5 equals to 375 plus 50 times 2 equals to 100 Newton meters. So 480 plus 375 plus 100 equals to 955 Newton meters. Okay. So at this stage again, it's reaction left times 10 meters is equal to 955 Newton meters. So just to help us again, it will be reaction left times 10 meters. We want to get rid of the 10 meters so that it's on the right hand side. So this one is multiplied by 10. We will divide by 10 on the left and the right side to get rid of it on the left hand side. So reaction left is equal to 955 Newton meters divided by 10 meters. Meters cancels with meters. So 955 divided by 10 equals to 95.5 newtons. Okay. So this is the two final values for reaction left and reaction right. So here at the top we will just add over here again. Reaction left equals to 95.5 newtons. Just that it stands out a bit. Okay. Now at this stage, that's the nice part about these calculations, is at this stage, after you've calculated reaction left and reaction right, you can check yourself. Because remember, this beam is in equilibrium, meaning that the downwards forces is equal to the upwards forces. So the downward forces is 60 plus 75 plus 50. Those three forces going down, added together is 185. So now, if we add these two, they are supposed to be the same value. So 95.5 plus 85.5 is equal to, sorry, made a mistake there, 95.5 plus 89.5 is equal to 185 newtons. So at this stage, we are guaranteed to have, let's have a look here. Here you would have 1, 2, 3, 4 marks. For this one, you would have 1, 2, 3, 4 marks. For this one, you are guaranteed to have 8 marks at this stage. Just be careful that you did not swap around reaction right with reaction left. If these two are swapped around and you labeled your question numbers according to how they asked it, but you didn't keep in mind that in order to calculate reaction right, you are working around reaction left. If you swap those two around, unfortunately, you might not get those marks because the marker only marks strictly according to the question number and the calculation that you did under that question number. So just be careful of that. Okay, so now that we've calculated reaction left and reaction right, we can go and calculate the bending moments. So the bending moments are normally they don't ask you to show the bending moments at A and at E, or the first and the last ones. Just be careful also, sometimes the labeling of A would start there. So it would be the bending moment at RL, A, B, C, RR. But in this case, A is also reaction left and E is also reaction right. Okay, so again, we are preparing for the worst of the exercises or worst of the questions. So we will show we will show what the value of the bending moment is from A up to E. So firstly, the bending moment at A, let's list that one so long. Okay, bending moment at A. A bending moment, again, the moment at the top, make a note this for yourself. The moment is equals to a force times a distance. So normally when I explain this, think about a ruler. This would be point A, which is the one at the left, and then a bit to the right side, that would be point B. What causes this point to be bending or to show a bend in the diagram? It would normally be an external force pressing down on it, not the point over here, because then the beam itself would move up and down. If this is a fixed point and there's a force pressing over here down, then it's going to cause the bend in the bending moment diagram. The same towards the right side, if there's one over here, presses down, there's going to be a bend in the diagram. Even further on also. So we have to keep in mind the sum of all the bending moments on the left or on the right side. So remember, it's the force, the external force, which has an influence on the bend. So at A, there's no distance towards the left, and there's also no force towards the left. There's only a force at point A. So any value any value multiplied by 0 will be equal to 0. So we already know at A, the bending moment will be equal to 0 Newton meters. Keep in mind, a moment is Newton meters. So at the end of each answer of each value, add the Newton meters units. Okay, now for B. At B, we have to calculate the bending moments. Again, it is the sum of the external forces having an influence onto that point. So the force we will not be looking at the 60 Newton, because that is the force at B. We want to look at the forces either to the left or the right side times the distance. So over here we've calculated reaction left, which goes up over here, times the distance up to B. So it's 95.5 times 2. Keep this in brackets for now. 95.5 newtons times 2 meters. Okay. We could also have, instead of working towards the left, we could have worked towards the right. But we can see that there's 3 more forces on the right side compared to the left side. So the easier way to do the calculation would be to the left. But if we did it towards the right hand side, remember we're not looking at 60 Newton because that is at B. So we are looking at the external forces. There's one upwards force over here times the distance, one downwards force here times the distance, and one downwards force here times the distance. So if the force is upwards, it's positive. If the force is downwards, it would be a negative value. So we will be doing it in that way as soon as we get to C and D. Just keep in mind, you can choose either to working towards the left or the right side, whichever is the shortest route towards the external forces. Okay, so let's carry on with this one for now. B would be equal to 95.5 newtons times 2 meters equals to 191 Newton meters, because we were working with a value of Newton times meters. Okay, now for C, the bending moment at C. C is exactly in the middle, so now we can choose, are we going to work towards the left or work towards the right? To calculate this, we have to work or multiply the external forces, external moments, sorry. So the force times the distance, and there's another force times the distance. But if there are 2, we will have to add those 2 moments to each other. Okay, so let's work from the left-hand side, as we did with point B. So on the left-hand side of C, that's what we want to calculate. On the left hand of C, there's one downwards force, the 60 Newton, and one upwards force, the 95.5 Newton. So let's start on the furthest on the outside, the left. It's an upwards force, that will be a positive value, and we are working with moments. So it's the force, positive force, times the distance up to C, so it's 5 meters. So work with brackets, open the bracket, 95.5 Newton times 5 meters. Close the bracket. So here it's a force, positive force times the distance up to C. We close the bracket, and remember it's the sum of the external moments. So we will have outside of the bracket a plus, open the bracket for the new moment, and then it will be downwards force, which is a negative force, times the distance. So it's minus 60 times 3 meters. Minus 60 newtons times 3 meters. Okay, then we will have to calculate this. So it's 95.5 times 5 equals to 477.5 Newton meters. Positive times a negative value will be a negative value. So it will be minus 60 times 3 equals to 180 Newton meters, which equals to 477.5 minus 180 equals to a value of 297.5 Newton meters. Okay, so that is the value for B, that is the value for C. Okay, next we have to calculate the bending moment at D. Okay, so the bending moment at D, we're going to have a look what is the shortest route either to the left or the right side. In this case, the right side would be the shortest route. So we could say 85 newtons times 2 meters. Positive 85 because it's an upwards, 89.5 newtons because it's an upwards force times the distance of 2 meters. The sum of the external moments. There's the external force times the distance up to D. But for explanation purposes, I'm going to do it towards the left so that you can choose either from the left or the right side. If you're working from the left hand side, it is the longest route, but I think it would be good just to understand it in this way as well. So working towards the left from point D, there's 1, 2, 3 forces. 1 upwards force, 2 downwards force. So it will be a positive force, negative force, negative force. All of these respectively the distance toward point D. So the furthest one will be positive 95.5 Newton times 8 meters. We will put this in brackets. So it's just a look here, 95.5 newtons times 8 meters plus, remember it's the sum of the moments, so outside of the brackets it will be a plus. Open the bracket for the next moment. So we're working towards D. We've already added or written down this moment, positive 95.5 times 8 meters. So now it will be minus 60 times 6. Minus 60 newtons because it's downwards times 6 meters. Minus 60 newtons times 6 meters plus, open the bracket again for the last moment. So the last one will be 75 Newton, minus 75, sorry, because it's a downwards force, minus 75 times 3. Minus 75 newtons times 3 meters. Okay, so over here, 95.5 times 8 equals to 764 Newton meters. Plus the second, sorry, that will be a negative because positive times a negative is negative. So minus 60 times 6 equals to minus 360 Newton meters. And again, it's positive times a negative. So it will be minus 75 times 3 minus 225 Newton meters, which will be equal to 764 minus 360 minus 225, which equals to 179 Newton meters. 179 Newton meters. Okay, so there is the bending moment for D. The last one would be E, and again, that one is on the edge. Any distance towards the right side is 0 meters, and any force on the right side is also, there's no forces, so it's 0 Newton. So the answer would be anything times 0 equals to 0. So if it is one of the questions, E will be equal to 0 Newton meters. Okay, so we have all the bending moments at this stage. Now we have to go and write down or draw the bending moment diagram. Okay, so for this, there is supposed to be a scale given. So we will start with, let's do it over here. The given scale for the bending moment diagram is 10 Newton meters is equal to 1 millimeter. So we're working with this one over here. The scale given at the firstly over here was for the width of the beam. So 1 meter equals to 10 millimeters. So that 2 meters would be 20 millimeters or 2 centimeters, 3 centimeters, 3 centimeters, and 2 centimeters. Make sure that this width of the beam is drawn according to the given scale. And then for the height, so we have the width of the given beam. Get the habit of then drawing the divisions of the distances down with a pencil, because these are the vertical distances between the bends in the bending moment diagram. But the vertical heights will be according to this scale. Okay, so it is sometimes a gamble just to decide where your beam will be to make sure it fits on the page. My suggestion is normally start at the bottom of the page and then you work up. but just make sure there's enough space, meaning that the calculations does not interfere with the actual beam. So it would be safer to start on the next page, but always have this sketch close by for your calculations, because you're referring to this beam when doing these calculations. Okay, so to do the bending moment diagram, we are going to start with a 0 Newton meter line. So we will start by drawing a horizontal line over here. And firstly, this will be the 0 Newton meter line. Start by labeling it over here 0 Newton meters on the right hand side, and on the left side 0 Newton meters. So now from here, everything will be going up. The bending moment will always be positive. So you can have a look here from 0 Newton meters, it's positive, 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 well, 0. So nothing will be below the 0 Newton meter line. So now at A, which is this one here, let's label it A, B, D, and E. Okay. Again, keep in mind, A was there straight down, that would be A. B straight down, that would be B. Just keep enough space between the 0 Newton meter line here and the beam to make sure your beam will fit in over here. Okay, so it starts at 0. It starts and ends at 0. So it will be going up, jumping around in between, but it will end at E again at 0 Newton meters. So B is 191 Newton meters. So we will be working with this value and the scale at the same time. So on your calculator, 191 divided by our scale, which is 10 Newton meters, that will be so many millimeters. So it's 19.1 millimeters. That will be, it will be going from 0 Newton meters going up. So 19, yes, make sure you do your diagram in pencil first, because if you make a mistake, you're going to have to start a new one, and then you might waste some space over on your page. So start by doing it in pencil, and then when you're done, you can go over in pen. So 19.1 would be over here. So that would be from 0 up to B would be going up. Then make sure you label this point. You might not get your mark if you did not label the value of 191 Newton meters at that point. The next one would be 297.5 newtons, 297.5 divided by our scale, which is 10 Newton meters equals to 1 millimeter. So the answer here would be 29.75 millimeters that it goes up from 0. So you're going to start over here on the 0 Newton meters line. So that's very close to 3 centimeters, and that would be where it goes to. So over here, remember to label it. Don't write down the millimeters value. You have to write down the value of the Newton meter value. So that is 297.5 Newton meters. Now for point D, at point D it's 179 Newton meters. So in your calculator, 179 divided by 10 equals to 17.9 millimeters. So from 0 it goes up 15, 16, 17, just a bit towards the side. There you are. And that is 179 Newton meters. And then from D, it's supposed to return back to its starting position, which is 0 Newton meters. Okay, so now the last thing to do for this diagram is to put in the hatching. This you can do with a ruler. You can also do it freehand, but let's just add it here. just to fill up the space of the diagram in between the values at the top and the 0 Newton meters line, which is the horizontal line over here. Okay, if you want, you can go over with a pen, just to make sure everything is nice and dark, or make sure your pencil marks are dark enough. The values or the marks are normally given here in the following manner. If your the horizontal widths are correct according to the given scale over here. So that's why I say it's safer to draw your beam on scale at the top and then draw the lines going down. So if your values are drawn according to the correct width, there's normally 1 mark. Then for the 0 Newton meters line, there's normally another mark, and then 1 mark per value in between the 0 Newton meters line. So this mark is for that one, for that one, for that one. That's for the 0 Newton meter line, labeling all the points, and that one is for the widths of the beam. So this one would be 1, 2, 3, 4, 5 marks width. Okay, so now, as I mentioned in this question paper of, I think, 2024 November, this was all that was required to complete. But always prepare for any type of question or a full question. So anything else that they could have asked in this calculation was to calculate the shear forces, and then also to draw the shear force diagram. So we'll be doing that in further preparation for future questions similar to this. So the shear forces, the word shear forces, it only has to do with forces. We are not going to look at any distances or meters over here. With this one, we had bending moments. A moment is a force times a distance. The values here was Newton meters. In this case, the shear forces will only be in newtons. Okay, keep that in mind. So we have to calculate the shear forces at point A, B, C, D, and E. So we will label them all over here, A, B, C, D, and E. Okay, so at A, this is normally where the confusion comes in. At A, yes, it goes up to 95.5 newtons. So, but the answer would not be 95.5 newtons, because it started on the 0 newtons line, and then at point A it also goes vertically up 95.5. So it starts at 0 newton, and then also at that point it goes up. So we're not going to consider the 95.5 for point A, but for B and C, D, and E, we will have to consider the 95.5 going up. Okay, so now for B, at B, we have to consider all the external forces. So in this case, all the external forces up to point B. So for B, it goes up 95.5 newtons, and then it goes down 60 newtons up to B. So it's positive 95.5 minus 60. That's still in newtons, so it's 95.5 minus 60 equals to 35.5 newtons, because it's shear forces. We're only working with the newtons. Next, for C, so it's 95.5 newtons minus 60 newtons minus 75 newton. In this case, it's the external forces up to that point, up to and including the point that we want to work or calculate. So it's positive 95.5 minus 60 minus 75. 95.5 minus 60. Just take note here. Those two values are the same. Those two values are the same. But now we're just adding another one, which is the 75 newtons. So it will be equal to minus 39.5 newtons. Okay, next for D. D working towards the left, it's 95.5 positive, minus 60, minus 75, and then minus 50. It's included, minus the 50. So it's 95.5 newtons minus 60 newtons minus 75 newtons minus 50 newtons. So the 50 newtons is the only one that came in for D. So 95.5 minus 60 minus 75 minus 50 equals to minus 89.5 newtons. Okay, now for E, and this again is one of the ways that you can check yourself if you did all of these steps correct. So now we're going to add another one, because at E it was positive 89.5. So we're going to working towards the left hand side, so it's positive 95.5 minus 60 minus 75 minus 50 plus 89.5. So we'll write down all of these ones, and if we were correct or working correct up to this point, we are supposed to end up with an answer of 0 newtons. So it's not positive 95.5 minus 60 minus 75 minus 50 plus, because E is a positive value going up, plus 89.5. Okay, and then if we working out this value, we will get to an answer of 0 newtons. So if you followed all of these steps and you came out to an answer of 0 newtons, you can be quite sure that you got all of your marks over here. So over here, let's just quickly go through. We'll get a mark over here, mark over there, mark over there. There sometimes is one of the required questions, but not the past few years it was not one of the questions. So normally this would count 3 marks. For the bending moments, I forgot to do this. So for the calculation where everything was in the brackets, that's normally with 1 mark and then the final answer 1 mark. So there would be 1, 2, there would be 1, 2, and then for 0 newtons, normally there's not a mark given. So 1, 2, 3, 4, 5, 6 marks for this. Okay, now that we've calculated the shear forces, we will be drawing the shear force diagram, which is the last part of this exercise. So for this, let's quickly check a scale that we can work on for this. Okay, so the scale that we will be working on for the shear forces, that would normally be given if it was one of the questions, but let's work on the following scale of 20 newtons is equal to 10 millimeters. Okay. So this scale is only applicable to the shear force diagram because the scale is given as Newton, a Newton value towards a millimeter value. Okay. So unlike the bending moment diagram, the shear force diagram has positive and negative values. We can see over there that it is positive, negative, negative, and back to 0 newtons. Okay, so we will start with a 0 Newton meter line, the same as what we did with the bending moment diagram. Start with a 0. Here we started with a 0 Newton meter line. Here we will start with a 0 Newton line, 0 Newton line, with points A, B, C, D, and B. Okay, so remember that I mentioned over here that at A, the shear force starts at 0, but then it also at that point goes up 95.5. So yes, it starts over here, but then it goes vertically up 95.5 newtons. So typing in our calculator 95.5, that's the value of the given distance that it goes up. We have to consider the scale that's given, 20 newtons divided equals to 10 millimeters. So we can simplify this a bit for ourselves by saying over here, we know that 10 millimeters equals to 1 centimeter. So I'm just going to do it like this by saying 20 newtons equals to 1 centimeter. So you can choose whichever way you prefer to work this on, but this, you can agree with me that this means exactly the same thing. I'm just going to do it this way so that it's easier to read it all from the centimeter ruler. Okay, so we have the 95.5 newtons that it goes up, divided by our scale of 20. Just want to get this one up a bit. Okay, so divided by 20, which is our scale, equals to 4.775, so it's 4.775 centimeters that it goes up. So it overlaps a bit with my calculations, that's fine. So it will be going up over here, this distance vertically, and then it stops over there. Then it stays horizontally the same up to B, which we will calculate next. Just remember to add the value that we just plotted, that it goes up here, 95.5 newtons. Then the next one, we have to consider that it goes down 60 newtons. So if we subtracting the 60 newtons, we are getting the 35.5 newtons. So the distance that it goes down is 60 newtons, but we are supposed to end, if we read it from the 0 newtons line, going up at 35.5 newtons. So we're going to type in over here 35.5 divided by our scale, which is 20, which is 1.775 centimeters. So here, it's around about 1.8. From the bottom that it goes up, this is 35.5. That distance is 60, which is that value that it just went down. So this will be a line going down up to B, which then stays horizontal up to C, which we are labeling as 35.5 newtons. It's a positive value, so it stays above the 0 Newton meters line. So then at C, it falls down 75 newtons. So it falls all the way, and then it's going into the negative. We've already calculated here that at C, it's supposed to be ending at 39.5 newtons. So minus 39.5 divided by our scale, which gives us minus 1.975. So it's around about minus 2 centimeters. So it will be from the 0 Newton meter line, from the 0 Newtons line, going down 1.97 up to there. So then from B, it's a straight line going up to this one, and then horizontal line staying the same height up to D. Over here, you're going to add the minus 39.5 Newton value, and now we have to check whether this one goes up or if it goes down. So at this same point here, following it up, it goes down another 50. So from this point, it goes down 50, but we already plotted here the minus 50, that it ends at minus 89.5 newtons. So minus 89.5 divided by the scale of 20 equals to minus 4.475. So from the 0 Newtons line, align your ruler, goes down 4.475. That will be a line going up to that point, horizontal up to E, and then at E it was supposed to be added by 89.5, which is a vertical line ending at 0 Newtons line. Keep in mind, or remember to add your value here of 89.5 newtons. Okay, so there's our shear force diagram. We just have to add the hatching for the beam. Okay, so for this beam, the same as with the bending moment diagram, here for the 0 Newton line, you would be getting 1 mark. For the width, there would normally also be a mark if your width was drawn on the correct width as given in the scale over here, which is why we drew the diagram, the beam at the top, so that we can draw those lines going down. So there's 2 marks, and then for each of these values, there's normally 1 mark. So it's 1, 2, 3, 4, 5, 6 marks. But then also there would normally be another mark, almost like a bonus mark, sometimes given if you put in your hatching. So that would normally be 7 marks. I forgot to mention with this one, we gave the mark here for the 0 Newton meter line. So that's 1, 2, 3, 4, 5. But also there's normally 1 bonus mark for the hatching, if the hatching was done correctly. It might not always be there, but always add in the hatching for the diagrams, for both the bending moment diagram and the shear force diagram. Okay, so if we add all of these marks, the 4 for the 8 for the reaction left, reaction right, plus the 6 for the bending moments, plus the 3 for the shear forces, plus the 6 for the bending moment diagram, plus the 7 for the shear force diagram, this can actually count a total of 57 marks. But yeah, it's not going to happen that all of these are asked, because remember, question 7, which is the question in your question paper about forces, it's a question which is count 45 marks. And this is just one of the 3 types of calculations that you get in question 7. It's normally these ones, the beam calculations. It's normally the stress and strain calculations. And then it's also the framework structures or Bose notations. So all 3 of those types of questions has to add up to a total of 45. And this one calculation alone overlaps already the 45. So always prepare for the worst of the exercises, meaning that they can ask you all the type of calculations. But yeah, the more you practice these calculations, and then also the more you prepare for the worst of the type of exercises, the more prepared and better you will get in the exam.